for Mario 64. So for this I set up a Yoshi right here. He has behavior 4538, the regular Yoshi behavior, and if you look at this behavior, like in my behavior scripts.txt, the Yoshi behavior is in this place, which is exactly here. It's a modified behavior. It's basically, well, I assume you've already watched my behavior script tutorial. If you haven't, you should do that first. So it's a start object, calculate distance and set rotation, animation pointer, interaction type, collision size, then we animate him, and then a loop. So for now I just want to make an empty loop like that and show you what happens. We just have a regular Yoshi standing here looking at you. So we want to make him do things to show you how assembly coding works. Now the way you call assembly code in your custom behavior is you put a 0C comment, and then this is the address of the assembly code. Now you don't know where the address for the assembly code is. For most codes, like everything in the checksum area, the checksum area is something from 0x1000 to 0x100000. Everything that is in ROM in here, or most of it, is in the checksum. So if it is here, this gets loaded in RAM to 802460000 to whatever, to the end. So what that means is that if you have a RAM address like this, you see that this is actually 8024500 higher than the ROM address. So what you can do is you just take this minus 245000, and this is the address where you want your code to be. And this is what we're going to do. We write .org 0x and then the address for our code. This is where our code starts. Now, this is where the old Yoshi code was, so I know that this is empty space. If you yourself want to make your own code, you will have to find empty space by yourself. The best way to do that is if you go in lemASM and then you open your ROM, say this one. Let's take our Yoshi address, we go here. We see a bunch of stuff, right? This is all the Yoshi code. And if you scroll down until you see JRRA, like JRRA, like this, that means the code is over in the next line. So if you scroll down here, we see we have space to B3F000. So that's like, I don't know, 30 lines of code that we have. So we can just safely overwrite this. This goes for any object. Now, I'm gonna be showing you how to do this for KajeASM. I'll put a link to KajeASM in the description. Anyway, for KajeASM we have to put a exclamation mark main at the very beginning for my version. The later ones probably don't. So first of all, we're gonna start off our ASM code by doing this. I will explain what exactly this does later. This is not as important now. We need this at the beginning of the function, and we need at the end of the function, we need this. Yeah, I'll explain what it does shortly. But before we do that, we go into simpler stuff. First of all, we need to, like what we want to do, we want the Yoshi to just rotate around the y-axis, a very basic thing. For that, we need to assess the Yoshi's y rotation value. And to do that, we first need to find out where in RAM Yoshi even is. Now, what this behavior is called, like what this behavior is running, the game stores the pointer to the object to 8036, like it stores it to 80361160. So we need to load from this address. To do that, we need to use two instructions. First of all, Louis T1 8036. Now what does this do? This Louis means load upper immediate 8036 into T1. So this results in T1 being 80360000, hexadecimal obviously. So you can load 4 digits, and it's the first 4 digits of the register. The register can hold 8 digits in hexadecimal. Next off, we need LW T2, let's use T2, 1160 from T1. What does this mean? It means load word, which word is 4 bytes, into T2 from 0x1160 plus the content of T1. So basically we load a word, basically we load a word from 80361160 into T2. So now we have the pointer to Yoshi, like Yoshi's address. This is where Yoshi lives in our Mario 64 RAM. We have that in store. Now we also need to address his rotation value. Now the easiest way to find out where his rotation value is to just go to Kaze Mario 64. I have a site here called structs, and you still see object struct. This is what we've just assessed. Like, we have a pointer into this, and now we just have to scroll down to the rotation. This rotation, we need rotation too. This is the movement rotation, like the direction of the movement, and this is the direction of the model. The Y rotation is at 0x_d4. So what we do, just like here where we loaded T2 into from 1160 plus T1, we want to load from 00d4 plus T2, because we already have the Yoshi's home address, which is in T2, and we just need to add d4 to it to get to the home address of his rotation. This is where his rotation lives, basically. That's how you can think of it. So we will load this into T3, 00d4 from T2. You already know what this means, just like it's the exact same as this, but this time we load the rotation instead of the pointer. Now a new comment, add u T3 0200. What does this mean? Add immediate unsigned. We add an immediate number, but we add the content of T3 with 0x200, and store the result in T3. To make that more clear, and store the result in T4. So this is where the result gets stored. This is what we want to add, and this is also what we want to add. So now in T4 we have Yoshi's rotation plus 0x0200. So in Mario 64 a full rotation is 0x10000, and we've just added 0x00200. So as you can see, this is just a little part of our full rotation. And now we want to SWT3 00d4 from T2. This just means store word from T3 into 00d4 plus T2. So basically right back into the rotation. Let me kill the... Let's just comment this out, I hope this works. Yeah, you can't just comment this out. KazeESM doesn't like that, okay. Let's remove that. Okay, shut up. Assemble, okay. Let's run this. Now Yoshi should rotate in a circle. Right, this is the error you will also get. If you don't want to get this error, you need to take this ROM and drag it over checksum64.exe or disable the checksum check in the level importer. That's KazeESM also does that automatically, but only like a fifth of the time, so I just roll with this. And Yoshi is absolutely not rotating because... Oh, right, okay. Yeah, I accidentally stored T3 again. Okay, don't do that. Drag over checksum. Yeah, I have notes on the other side and it used T3 there, so I had to quickly adjust it. Okay. So a full rotation takes around 2 seconds now, which makes sense, 64 frames. This is like if you multiply this by 0x40, which is 64, you get a full rotation. Alright, now say we want Yoshi to make a sound every quarter rotation. It sounds really stupid, but let's do it. Now for this, how can we actually find out whether we've done a quarter rotation? It's actually put to 0x1, so it doesn't talk too much. Yeah, how do we find out if he's done a quarter rotation? So the rotational values, the way we have it now, first they are 0, 0, 0, 0, then they are 0, 1, 0, 0, 0, 2, 0, 0, and so on, right? All the way to 0, 0, 0, and then they go to 0, 1, right? And this goes on all the way until we reach 3f 0, 0, and then 4, 0, 0. Now, this is when we have a full quarter rotation, and something interesting happens here. If you look at the bit representation, if you write this in bits, for this one you get 0, 0, and then a bunch of ones, right, and then more. And for this one you get 0, 1, and then a bunch of zeros, right? And until we are here, the ones just pile up afterwards, and afterwards, after we add here, the ones all disappear. So we can abuse this bitwise representation by doing AND E T5 T4 3F00. Now 3F00, as we mentioned, 3F00, let's write it down actually. 00, 11, 111, 11, and then a bunch of zeros. They don't matter anymore. We don't edit these. Blah blah blah. And then afterwards, right? So, and then when we add the next number, we are at this again, right? Until we have a full quarter rotation. So every time all these numbers are 0, we want it to play a sound. So if we end it with this number, it will be exactly 0 whenever we finish the full quarter rotation. So for this reason, E and E T5 are 0, no sound. We go to the no sound label. Let's put the no sound label here, and here will be code for playing sound. Okay, what does this do? This means branch not equal T5 R0 to no sound. If T5 and R0 are not equal, it will branch, meaning jump, to the no sound label. What is R0? R0 is a register that is always 0. It's always 0. No matter what you do, it's always 0. Yeah, we have registers R0, T1, T2, T3, T4, T5, T6, T7, T8, T9, and that's all you need for now. That's all we will do in this tutorial. The other ones, they are a bit more special. Not really, they are all the same, but the programmers use them in a special way. Anyway, now we want to play a sound. You will ask yourself, how do I play a sound? Well, you go to mist and sound. Let's Google that. Play sound. No, I don't like this one. Let's use play sound properly. We take this function and we use a command called jal. What does jal do? Jump and link. This one jumps to an address and stores where the code just was in a special register called RA. This is where I explain what this and this does. Each instance of code, like whenever you run somewhere, you have a stack pointer. And the stack pointer, you use that to store variables that you can't lose. Like right now, this would jump into a totally different part of the code, and it would do comments like these all over. And that would ruin every register we have. Like in T2, we wouldn't have Yoshi's home address anymore. We would just use Yoshi's home. We wouldn't know where Yoshi lives anymore, and we couldn't visit him. We couldn't change his rotation. We can't have that happen. So for that purpose, we have a thing called stack pointer. This always stays consistent. This is a RAM address where we can store whatever we want. And this function, this will like do this kind of thing too, where it subtracts something from the stack pointer. Like right here, we subtract 0x18 bytes, exactly the inverse of this. And then we store this to 1/4 from the stack pointer. So we've reserved 0x18 bytes for our own temporary addresses, and we can put whatever we want. Like, let's say we don't want to lose Yoshi's home address. We could just do SW T20010 from SP. And now, after we've injalled the play sound function, we could just LW T20010 from stack pointer, and we'd get our Yoshi pointer back if we wanted to do something more with Yoshi afterwards. And then at the end of the code, you reload RA. This means return amount, by the way. This is just where you want to return. You execute JRRA, meaning you jump to the return amount, and then you add to the stack pointer. Now you'd think that this needs to be in this order, which makes sense, and you are correct usually. But in this special instance, we use MIPS R4300I. It has a delay slot after each jump. That's why we have a knob here. Whenever you jump anywhere, you need to delay by one slot. I mean, the next slot of code, it also executes. So right here, technically, we need to put a knob, because otherwise we first load T2 and then we play a sound, and then we would lose our Yoshi pointer, or Yoshi home address again, and we don't want that. So now there's more to this. If you look at list again, sound, it says we need A0, a sound value. Now for the sound values, this is rather uninteresting. You just go into play sound. It's just a special convention. Let's use the Yoshi sound. And A0, you need to put this. Now sounds wants A0 this, and don't ask why. This is just how the function works. This is how the Mario 64 program has decided it. So now, every quarter rotation, Yoshi should do his little twiggy thing. Let's listen to it and see if it works. There you go. Yeah, just to show you that we've just recovered the Yoshi pointer right here. We could do like LWT3000 from T2. 00D4 was this Y rotation, then this is this X rotation. It always gives X, Y, Z in Mario 64. We add like, I don't know, 0800 to it and we store it right back. And now every quarter rotation, Yoshi will do a sound and rotate on X. X is a bit, and it will look really stupid. Yeah. Alright. I think that's enough for the first tutorial.